Welcome to the second lecture of this week in EE557. Hopefully this is going to be also the last lecture of this course. In the previous lectures we have seen the optimal control of linear Gaussian systems when with complete information, meaning that yk is equal to xk, when the output is equal to the perfect knowledge of the state. And we have also seen the estimation for linear Gaussian systems. In this last lecture, we're going to try to combine these two theories. So what happens when we try to optimally control a linear Gaussian system with partial information, meaning that when the measurements are actually different than the knowledge of the state. So if we have only partial information of the state, then of course we will need to combine the estimation theory with the optimal control theory. And the resulting feedback controller is going to be based on the estimates that the Kalman filter is going to calculate. Okay, so let us start with the topic of this last lecture. So the title is quite long here. So we have optimal control of linear Gaussian. I can write LG here. Linear Gaussian systems with partial information and quadratic cost. So this is our title, and in the control literature, this topic is called as linear quadratic Gaussian control. Okay, so we have a linear system, we have a quadratic cost, we have Gaussian noises, and then we would like to optimally control such a system to optimize a quadratic cost. So you all know now what the equations of such systems would look like. So I have this GWK, and YK is equal to CXK plus I have HVK with the measurement noise. And in this case, in the earlier case of the optimal control for such a system, we had YK is equal to XK. Okay? That means that the outputs are exactly equal to the states. So we can observe the state perfectly. And that is the case of complete information. And in this case, we have non-complete information or the partial information where the outputs are not going to be the perfect state, but a function of the state, c times x. So we can choose some linear combinations, we can observe some linear combinations of the state variables plus some measurement noise. So we don't observe the linear combinations of state with no noise still. There is still a measurement noise. So we have really partial information in this case. And in the earlier case of optimal control for this type of systems, we also had UK is equal to GK XK. Okay, this was the feedback rule that we used in the earlier theory. Here, we're going to change this because we can no longer observe the state perfectly. So we won't have this information xk when we try to control the system. Instead, we are going to just have current and the previous measurements available to the controller. Okay? And I have the partial information, I have the feedback control, which I'm going to try to choose optimally. And of course we have the classical initial state distribution and process noise distribution and measurement noise distribution. Okay, and of course I have still the independence assumption here. X0 and WKs and VKs are independent. So when we talk about optimal control, of course we need to talk about the cost function of this optimization. And that is going to be looking like this again, a very similar thing. It should be now to you. K from 0 to n, CK, XK, UK. Okay? We know that such a quantity is stochastic, so we are going to try to minimize the expected value of this thing. All right? So now we know that this is going to depend on the feedback law, so I can put here a superscript G. In this case, in the title, we also have the adjective of quadratic. So these cost functions can be arbitrary in general, but with general cost functions, we don't have closed form solutions for the control, as in the case of the quadratic cost. So here we are going to be considering only the quadratic cost. But of course, in general, these CKs are arbitrary functions of xk and uk. So here we have ck of xk uk. We are going to have xk transpose mk xk plus uk transpose pk uk. Okay? And this is true when k is between 0 and n minus 1. And when k is equal to n, I have cn of xn un is going to be independent of un. I don't want this un to be in my optimization. So this is going to be only a function of xn, because un is going to affect the states starting from xn n plus 1, n plus 2, etc. Okay? So this un, I would leave it outside my optimization horizon, and I would have just cn xn in this case, and that is going to be equal to xn transpose mn xn. So in the lecture that we considered the control of this system with complete information, here we defined a similar functions for ck and cn like this, but instead of pk there I used rk. It was a stupid choice, or it was not a very good choice, because this capital R is used as the measurement covariance here, measurement noise covariance. So here, in the earlier case, we didn't have any measurements, any noisy measurements, and we didn't have any measurement noise. So in that case, it was acceptable to use RK as the coefficient matrix of this quadratic form of the input. But here, because we have noisy measurements and because we use the capital letter R for that purpose, I changed this coefficient matrix of the quadratic form of the input into pk. All right? So the first thing that I'm going to do here about this control is to remind you actually what we have seen for the complete information case. In the complete information case, we started with, let me write, complete information case. In that case, we had yk is equal to xk. We had perfect information of the state for all k larger than or equal to 0. And remember, in that case, we have first learned how to calculate the cost of a feedback policy. And in order to be able to calculate the cost of a feedback policy, we defined a recursion. And that recursion was based on a function, vk of xk. And that function was defined as follows. Vk of xk is equal to expected value. I have here L from k to n. I had CL, XL, UL, given the state at time k. Remember, this function was defined as the cost to go function. Okay? And then we could calculate the general cost, JG, for an arbitrary feedback policy based on these cost to go functions by defining a recursion for such functions. What was the recursion? we started with the Vn xn, which was equated to Cn xn, okay, which is this function. And then we have obtained a recursion, a backwards recursion for these functions. So we calculated Vk xk from Vk plus 1 xk plus 1, okay? And here I had Ck, xk, uk, and I had plus expected value. I had Vk plus 1, xk plus 1 here, given xk. This was the recursion that we obtained, backwards recursion that we obtained for this cost to go functions. And then we could calculate this Jg here as expected value of V0 x0. Of course, here this function is only dependent on x0. That means that I need to take expectation with respect to x0 here, okay, with respect to this initial distribution. So we start by calculating Vn first. There is no calculation here. We just equate it to the last incremental cost. And then we go backwards. Vn minus 1, Vn minus 2. We continue this recursion until V0. And then we take the expected value of V0 to obtain the cost that would correspond to the feedback policy G here. Okay? But this is only for calculating the cost for a given feedback policy. In order to be able to find the optimal feedback policy, then what we did was we optimized these cost to go functions with respect to the inputs. And again, we went backwards, all right? So let us write dynamic programming. This was called dynamic programming. And the dynamic programming idea was proposed by Richard Bellman, a very famous mathematician, and it is based on the so-called principle of optimality. The principle of optimality tells us that every part of an optimal policy should also be optimal. So there is a philosophical idea behind it, and in dynamic programming, that actually philosophical idea is shown by this V functions here. This is dynamic programming with perfect information. So far I'm only reviewing. So if you do not remember these parts that I have written so far, you need to go back to the earlier lecture that is related to the linear Gaussian system optimal control with perfect information. Okay? So this is, sometimes it's perfect, sometimes it's complete. They are the same thing. I have complete information. In that case, what we do is to calculate these optimal cost to go functions. Vk star xk is obtained as the minimization with respect to uk to n. Of course, I can write here uk to n minus 1 because the cost function will not be dependent on un if I define cn like this, but still it is the optimization with respect to uk to n in general, and I would have minimize the cost to go at time k. So I have L equals to k to n CL XL UL given XK. Okay? Since we are in an electrical engineering department, and since we are in this course is a course of the control specialty, we call this function as optimal cost to go function. Okay? But if we were in a computer engineering department, or if we were in a data science department, or a machine learning branch, in that case we would call this function as the value function. Okay? Terminology in different areas of study for this function is different. We call this as optimal cost to go function, but since machine learning is becoming more and more popular, when dynamic programming is used in a machine learning context, then this function is called the value function. And that is actually why we are calling this as capital V. Okay? So here, then we really do not like to do this optimization over multiple inputs at the same time. Okay? That is why we calculate these value functions also recursively backwards. Okay? We start with the last optimal cost to go function xn, which is again cn xn. There is no input here to optimize, so that is why we equate the last value function to the last incremental cost. And then we obtain the recursion. Vk star xk is equal to, I would minimize this recursion, the right hand side of this recursion. Minimize with respect to uk, I have ck xk uk plus expected value vk plus 1 xk plus 1 given xk. Okay? And the input that we find at the end of this minimization is the optimal feedback policy. And when I try to minimize this right-hand side here with respect to UK, I would get a UK in terms of XK. So at the end of this minimization, UK that I find would become a function of xk. Okay? This is coming because of the structure of these value functions. Whatever I put here into the given condition, the input that I find at the end would turn out to be a function of that given condition. Okay? So here when I find the UK star, in that case, it is the argument of the minimization with respect to UK of the same thing. And it turns out to be a function, gk, of the state, xk, the given condition here. And then I can, of course, find the optimal cost by taking this is j star. In that case, it will be just expected value of v0 star x0. And this expectation is again with respect to x0. Okay? So this was the general theory. Here I can use an arbitrary ck and I can try to apply this optimization idea to find optimal feedback policy. But in this lecture, we're going to be concentrating on the quadratic cost like this. Okay? In that case, we have seen that theory as well, and we have seen that this optimal input turned out to be a linear function of the state, xk. And it turned out to be actually uk star was equal to some gain, lk, times xk, minus lk times xk. So it was a linear state feedback rule that we obtained at the end of dynamic programming. So here, let us concentrate ourselves to the quadratic case. So I have the quadratic case. In this case, we have seen that this vk star of xk, they all turned out to be in the following form. xk transpose wk xk plus some constant beta k. Okay? And in that case, of course, we have also seen that we had this uk star turned out to be lk times xk. Some gain here, lk, times the state that we observe. This is, of course, wrong. It is also wrong in my notes, sorry. So I would have a minus sign here. Okay? This is minus lk xk. And here, how did we obtain this wk and beta k and lk? They were given to us in a backward recursion again. So for wk, I had the following recursion, backwards recursion. Wk turned out to be as a minus blk transpose wk plus 1, and I have a minus blk plus lk transpose pk lk plus mk. Okay? This pk is this matrix. In the earlier lecture we had the rk here. Now we had pk. Okay? And how did we start this recursion? We started it by setting Wn matrix to Mn, the last coefficient matrix of the quadratic form of the incremental cost. Okay? And beta was given to us in a backwards recursion. Again, beta k is equal to beta k plus 1 plus trace of wk plus 1 gqg transpose. Okay? And we started beta n from 0. These are the initializations for the backwards recursions, and this is the recursion rule here. And finally we had this gain lk was b transpose wk plus 1 b plus pk inverse b transpose wk plus 1 a. Okay? So this was the theory that we have seen so far. Okay? Here I would like to remind you something. Remember, in the case of perfect information, when yk is equal to just xk, the only randomness in the system is the initial condition and also the process noise. Okay? So we see that the process noise enters into the picture in the constants beta k. Okay? And we see that here this feedback gain lk is independent of beta k or beta k plus 1. So we see that here this feedback rule is independent of the beta k variable. Okay? So we can say that this lk is actually independent of the process noise covariance here. All right? So that means that the uncertainty of the system only appears in these coefficients beta k. Okay? And these w's are not affected by the randomness of the system. All right? This is the complete information case. So that means that whatever we choose this Q, whatever I choose this Q, the optimal control rule would always remain the same. The control rule that we find at the end, the optimal feedback policy that we find at the end is independent of the process noise covariance Q. What does that mean? That means, so what is different? What is different when I change Q? The value of the final cost is different. Okay? When I change Q, betas are changing, and because betas are changing, the value of the optimal cost changes. And actually you can show that if I increase Q, then the value of the optimal cost is going to increase because the system is then more uncertain, and in that case the cost that we obtain is going to be larger. All right? But the control rule or optimal feedback policy that we find at the end is independent of the process noise covariance. That means that even if I take this covariance Q equal to 0, I will get exactly the same control feedback policy. Okay? So what does that mean? That means that this feedback policy, optimal feedback policy, is also going to be the optimal feedback policy when I don't have any process noise in the system. Okay? But then I would have a deterministic system, and I'm trying to minimize some deterministic cost function in the deterministic case. That is called linear quadratic regulator. Okay? So here, the feed control policy that we find is actually also the control policy of the deterministic problem when the process noise is non-existent, and this is nothing but the linear quadratic regulator control policy or feedback policy. Okay? So changing Q does not affect the control policy, but it is going to increase or decrease the expected cost at the end. All right? So now this was so far what we have seen. Now I'm going to go into the partial information case, and we are going to try to repeat these parts for the partial information case. Okay? And in that case, we don't have complete information of the state anymore. Okay? We only have partial information, and that means that we need to use some estimator in order to be able to calculate an estimate of the state. So now let us see, cost to go with partial information. Cost to go with partial information. So as I told you, here, whatever is in the conditioning, our control law that we find at the end becomes a function of that condition. Okay? In the cost to go, whatever we put in the conditioning, the inputs that we find at the end of this minimization here becomes a function of that given condition. Okay? That actually gives us an idea to define some cost to go for the partial information case. We want our inputs, UK, in the partial information case to become a function of current and the previous outputs. Okay? We want our inputs, in the complete information case, we had GK, XK. In the partial information case, we want UK as GK, Y from 0 to K. Okay? So and here, this XK is nothing but the conditioning in the cost to go. Okay? So we are going to define the cost to go for the partial information case by putting this given information into the conditioning. Okay? That is how we are going to define our new cost to go for the partial information case. So I'm defining here V of, in this case, this cost to go in the perfect information case, we had XK here. In the partial information case, we are going to have V of Y0K. Okay? That is what the input is dependent on, is a function of. Okay? That is going to be equal to expected value L from K to N, and I would have here CK, XK, UK, and into the given, I have the same quantity here. Of course, I'm making stupid mistakes here. So I have CL, XL, UL here, and in the given condition, instead of XK, I'm going to put this by 0K. Okay. So this is going to be my cost to go in the partial information case. Okay? And hopefully, at the end of such a recursion and at the end of such a minimization, our inputs, optimal inputs, are going to turn out to be just a function of the given condition here, Y0K. Okay? So then the question is, in the complete information case, we could find the recursion for this cost to go, okay? What about the partial information case? Can we find a recursion for such a quantity, okay? And the answer is going to be actually yes. So here, in order to differentiate this cost to go in the case of complete information from this cost to go in the case of partial information, I am going to put the subscript here, k given k, okay? So this is the cost to go at time k given the information y0k, okay? So I will show the cost to goes in the partial information case with this notation just like in the Kalman filter. And now I'm asking the question, can I find a recursion for this quantity? And the answer is going to be yes. For that I'm writing vk plus 1 given k plus 1, y0 k plus 1 is equal to expected value L from k plus 1 to n, CL, x, this is the definition of vk given k, xl ul, and I have y0 to k plus 1, okay? This is vk given k, and this is vk plus 1 given k plus 1. The question is, can we find a recursion just like the complete information case about between these two quantities? And of course, I already said a couple of times the answer is going to be yes. Let us try to do it. So I have vk given k, y0k. This is going to be, I'm going to try to write this vk given k in terms of the right hand side here, all right? And for that purpose, I'm going to separate the L equals to k term from this summation. This is equal to expected value ck xk uk plus L from k plus 1 to n. I have CL xl ul given y0k, okay? And now I can distribute the expectation over the summation there, and that is going to give us expected value ck xk uk. In the earlier case, this k term got out of expectation directly because xk was given and uk was a function of xk. That means that I could take this term outside the expectation. But here xk is really not given to us. Only y0k is given to us. That means that I cannot take this term outside the expectation anymore, okay? Plus I have expected value L from k plus 1 n CL XL UL given y0k. So we are one step closer to our equation here. Obviously this first term is going to remain as it is, but I'm going to try to convert this second expectation into, or I will try to write the second expectation in terms of this expectation, vk plus 1 given k plus 1, okay? So for that, I need to change this conditioning. The conditioning in this expectation is y0k, conditioning in this expectation is y0 to k plus 1. So that means that into this conditioning, I need to add somehow yk plus 1, okay? So that is equal to, this first term is going to remain as it is, xk uk given y0k, and I will here again invoke law of iterated expectations. So I will write here expected value, I will put an additional expected value here, L equals to k plus 1 n CL XL UL. This term should remain the same, and in the outer expectation, I have this y0k. Okay? For the iterated law of expectations to actually hold, I need to always have the same conditioning here in the inner expectation as well. But into the inner expectation, I can add any variable I like into the conditioning. In addition to this, these should always be the same inside the conditionings, and I can add any additional variable into the inner expectation. And here I'm selecting this additional variable as yk plus 1. Okay, but you see that here in that case the conditioning in the inner expectation becomes y0 to k plus 1, and this inner expectation is nothing but vk plus 1 given k plus 1 now. All right? And that is going to be equal to expected value ck xk uk given y0k plus expected value of this inner expectation is vk plus 1 given k plus 1 of y0 k plus 1, and I would have the given condition y0 k. Okay? So you see that we could get our recursion here. So I have vk given k, y0 k is equal to this in terms of vk plus 1 given k plus 1. All right? Obviously, you see things are more complicated here. In the earlier case, I did not need any expectation here. And now in the partial information case, I need an expectation here in the first term. And furthermore, I had a second expectation. The second expectation did not change, only the given conditions changed. Now, what are these expectations with respect to? So I see that at the end of this optimization, or at the end of the optimal solution of the control problem, this uk is going to be a function of y0k. Okay? So as a result, in the first expectation, this uk is deterministic, because it's only going to be a function of y0k. All right? And y0k is given. So that means that this uk is deterministic. The only thing random in the first expectation is xk. Okay? So this first expectation is going to be with respect to xk only. Okay? Of course, I need to take the expectation with respect to xk given y0k. So I'm going to take the expectation of this quantity, thinking that uk is a constant, deterministic constant, and I need to take the expectation with respect to the density of xk given y0k. But density of xk given y0k is provided to us as a Gaussian from the Kalman filter. Okay? So here we see that when I try to take this expectation, I'm going to need to use the Kalman filter estimation results, posterior densities in that case. And what about the second expectation here? The quantity that I'm trying to find the expectation of is a function of y0 to k plus 1. Okay? And among these outputs, y0 to k are given to us. These are already given to us. Okay? So the only random quantity remaining here in the second expectation is going to be yk plus 1. So the second expectation is going to be with respect to yk plus 1. So of course, I need to take the expectation using the density of yk plus 1 given y0k. Okay? But this is the predicted measurement density that is calculated, that can be calculated using the Kalman filter results. All right? So here this is going to be my recursion, of course, but I would need also some initiation for that recursion. Okay? So I have found the equivalent version of this recursion in the partial information case. Now the only thing that I have to do is to find how to initialize that recursion. Okay? For that I'm going to calculate Vn given n. Okay? So Vn given n is going to be, this is going to be a function of y0 n, and that is going to be, I will substitute k equals to n here. Expected value of, if I substitute k equals to n here, the summation is going to be from n to n. So there is only a single L, which is equal to n. That means that I have here Cn. And remember, the Cn, xn, un was only a function of xn. Okay, so I would put this like this, Cn, xn. Okay? and I would have the given condition y0n. Now this is my initiation, and in this case the initiation is not as easy as in the complete information case. I need to still take an expectation here, and this expectation is going to be with respect to xn given y0n. But xn y0n, the density is a Gaussian with mean calculated using the Kalman filter, covariance calculated using the Kalman filter. So this expectation is actually with respect to xn given y0n. And finally, I need to know how to actually calculate the optimal cost at the end of calculating these cost to goes in the partial information case. So we're going to start with Vn given n. We're going to somehow take this expectation, and then we're going to go to n-1 given n-1, n-2 given n-2 using this backwards recursion, and then we're going to end up at V0 given 0. V0 given 0, this is going to be only a function of y0, and this is nothing but expected value. I have the whole summation L from 0 to n, CL, UL, CXL, UL given y0. That is the definition of V0 given 0, and we can find it recursively by starting from this and then going backwards in time. Okay? And what is our cost? Our cost is expected value of only this summation. K from 0 to n, CK, XK, UK. Here the summation variable, it really does not matter here, but we see that this cost here is going to be the unconditional expectation of this thing, but V0 given 0 that I find at the end of that backward recursion is going to be the conditional expectation of the same thing given y0. So then it is clear what we should do. If I take the expectation of this V0 given 0 once more with respect to y0, I am going to end up with my cost. Okay? But that is going to give us, again, law of iterated expectations. J, the cost Jg actually, is going to be just V0 given 0 y0 expectation, and this expectation is just going to be with respect to the marginal distribution of y0. Okay? So now this is the cost to go functions with partial information. All right? So now I'm going to go into dynamic programming with partial information. But in that case, you need to compare this theory with the case with complete information. What did we do in the case with complete information? In this recursion, we just optimized the right-hand side with respect to UK. In order to obtain the dynamic programming algorithm in the complete information, what we did was we got the cost to go function at time k, and then we optimized the recursion of the cost to go function, the right-hand side of it, with respect to UK. Now that is going to be what we are going to do in the partial information case as well. Okay? So I would erase this part. So dynamic programming with partial information. In this case, we are going to define Vk given k star, the optimal cost to go, which is the value function. This is going to be a function of y0 to k, and we are just going to define this as the minimum with respect to uk to n. And I will write here, I won't really repeat it, I will just write here Vk given k, y0k. Okay? So it is the, maybe I should repeat it. Okay? So I will just write it here, expected value of cost to go, k to k given k. And I have L from k to n, CL, XL, UL, given y0k. Okay? We define the optimal cost to go in the same way that we did in the case of complete information. Okay? But then we actually know how to calculate these optimal cost to go functions recursively. Okay? And what we are going to do is just, we are going to minimize the right-hand side of this recursion with respect to uk, and I would put stars here. Okay? Let us write that recursion. The first thing that I would do is to calculate Vn given n star y0n. In this case, in this last cost to go, there is nothing to optimize. There is no input here. So this is going to remain as it is. Expected value with respect to xn of Cn xn given y0n. Okay? And then comes my backwards recursion. We initialized our dynamic programming recursion, and then comes our recursion y0k star is equal to minimize with respect to uk, the right-hand side there. Expected value with respect to, here really I do not have to put these subscripts, but I'm putting them, these are not standard really, you won't find these in the books. I'm just putting them for the sake of simplicity so that you see what the expectations are with respect to, but really there is no such standard notation in the books. So I have ck, xk, uk given y0k, and I have plus expected value. This expectation is with respect to yk plus 1, vk plus 1 given k plus 1 star now. Okay? y0k plus 1. And I have given condition y0k. Okay? And finally, we can find the optimal cost j star as the expected value. In this case, this expectation is with respect to y0, v0 given 0, y0. And I have the star here. All right? So this is the dynamic programming equations for the partial information case. All right? So now we are actually ready for the specifying these cost functions. Now I know that my cost functions are going to be quadratics. Okay? Now let us specify the cost functions. So I would first start by actually calculating this initial cost to go in the case of partial information. Okay? So what was Cn xn? So here I can write the quadratic case. We have seen the general theory with partial information. Here C's can be anything. And now I'm specifying the C's into quadratic functions of state and the input. All right? So I know that this last, in order to initialize my recursion, I need to calculate this expectation here, and Cn xn here is Cn xn here is nothing but xn transpose mn times xn. Okay? Now I need to take the expectation of that quadratic form given y0n. So Vn given n of y0n is equal to expected value of xn transpose mn and xn given y0n. Okay? Now I need to take the expectation of a quadratic form with respect to xn given y0n. We have seen such an expectation rule in the past. So if I try to take the expectation of x transpose px, then such an expectation can be taken as this. X bar transpose px bar. I have just asked this in the quiz today. So I have here plus expected value, trace of p times sigma, where sigma is the covariance of x and x bar is the mean of x. Okay? Here, if I had such an expectation without any given condition, I would put here the unconditional means of this xn, and then I would use the unconditional covariance of xn in my expectation. But here, I had here a given condition y0 given n, y0 to n. Okay? So this formula is actually nothing but expected value of x transpose p expected value of x plus trace of p covariance of x. Okay? So this expectation formula is for an unconditional Gaussian distribution. And these are my unconditional expectations, and this is my unconditional covariance. Okay? So here, in my expectation, I have a given condition y0n. How should I handle that given condition? It is really easy. I will change this expectation here into a conditional expectation, expected value x given whatever condition I have, expected value of x given whatever condition I have, and covariance of x given whatever condition I have. Okay? So actually I can write this expectation quite easily. Vn given n, y0n is equal to expected value, I will just directly write the expected value. What is expected value of xn given y0n? That is the final Kalman filter estimate, xn given n. Okay? So I can run a Kalman filter on my system and I can actually calculate x hat n given n, and that is the mean that I need to put here. So I have x hat n given n times the matrix mn times the same estimate, okay? X hat n given n, my Kalman filter estimates, and then plus trace of this matrix mn times covariance of xn given y0n. What is that? That is the Kalman filtered covariance at the final time. Okay? Sigma n given n. Okay? So this is my final cost to go function, or the initial cost to go function. We are going to be going to backwards. So then this cost to go should be a function of y0n. Cost to go is a function of y0n. Where is y0n on the right hand side here? I know that these estimates, x hat n given n, is a function of the measurements from y0 to yn by the Kalman filter recursion. Okay? So Vn given n is a function of y0n through this estimates Okay? These estimates are a function of the current and the previous measurements. So as a result, the right-hand side is still a function of y0n, but that dependence appears in the form of Kalman filter estimates. Okay? We know that Kalman filter covariances are independent of the measurements. Okay? That is why this term does not depend on y0n, but the first term, of course, there should be a transpose here. The first term is dependent on y0n through the Kalman filter estimates. Okay? And this is actually Vn given n star at the same time. Okay? Because at the last time there is nothing to optimize. So Vn given n star is equal to Vn given n at the last time instant. So now in the deterministic case, we had seen that this Vk star of xk was always in the form xk transpose wk xk plus beta k. Okay? We had these optimal cost to go, those value functions, in the complete information case in this form. Now I want you to look at that last cost to go or initial cost to go. It really looks like this thing. Instead, I would replace these exact xk's by the estimates. Okay? So that is going to be the form that we are actually going to be using. All right? So let me find where I am. Okay, so let us assume that this Vk given k star of y0k, it is going to be, we are predicting that it's going to be in the form x at k given k transpose, I would have wk, and I have x at k given k plus some constant beta k. Of course, I can change the constant. They are going to be different, but I want to keep this the same to keep the similarity with that one. Okay. So if I assume such a form, then I know what Wn should be. W capital N is going to be Mn. But this was exactly what happened in the complete information case. And I would have beta n is equal to, in this case, beta n is not equal to 0 anymore, as in the complete information case, but it is equal to this constant, trace of mn times sigma n given n. Okay? So I found the initial values of Wn and beta n. Then if I know Wk plus 1 and beta k plus 1, how can I calculate Wk and beta k? Okay? If Vk given k has this form, then Vk plus 1 given k plus 1 star of y0 k plus 1 is going to be in the form x at k plus 1 given k plus 1 transpose wk plus 1 times x at k plus 1 given k plus 1, and I would have plus beta k plus 1. Okay? And I know the final values of Wn and beta n. Okay? And if I know wk plus 1 and beta k plus 1, I need to find the recursion which would connect wk and beta k to these quantities. And then I would start with these two, and then I would recurse backwards, doing the same thing that we did in the determinist in the complete information case. Okay? So now let us start our recursion now, or let us look at our recursion. So I will use this formula. Let us try to use that formula. So I have Vk given k star, and I have y0k is equal to minimize with respect to uk. There is minimization, so it's not going to be easy here. Expected value of, with respect to xk of this ck. Expected value, what was the quadratic incremental cost? I had xk transpose mk xk plus uk transpose pk uk. Here instead of rk I have pk. And I have of course the given condition y0k plus, we are not going to minimize only this thing, but the summation of two terms. Expected value, I have yk plus with respect to yk plus 1. And here, I need to substitute vk plus 1 given k plus 1 star. And I need to take its expected value with respect to yk plus 1 given y0k. Okay? But this vk plus 1 given k plus 1 star is already given to us like this. Okay? X set k plus 1 given k plus 1 transpose wk plus 1 x set k plus 1 given k plus 1 plus beta k plus 1, and I need to take the expected value of this thing given y0k. Okay? So this really looks challenging, probably the most challenging problem that we are going to solve in this course. So now let us start taking expectations. So I would have here this expectation is really easy. So I would have the minimum with respect to UK. In the finite state Markov chain case, we used infimum. Here I want to use just minimum because we are working with quadratic functions and we don't have any constraints. That means that the minimum of the function is always existent. So now here, when I look at this expectation, these UKs are a function of y0k. So these UKs are now deterministic. Okay? So this term is going to get outside the expectation directly because of the given condition. But what about xk's? Xk's are definitely random, and I need to take their expectation with respect to y0k. I would apply the same idea as I did here. So if I take the expectation of the xk transpose mk xk, it's going to be x hat, k given k, because of this given condition, mk, this is the Kalman filter filtered estimate at time k, and I would have x hat, k given k, and I would have a transpose here, plus the trace term, plus trace mk times Kalman filter covariance, filtered covariance at time k. That is what the covariance of xk is given y0k. Okay? Plus the input term is going to get out directly. All right? UK, and this is going to be what the minimization is going to be with respect to. All right? UK transpose PK UK. Okay? And now I come to the more challenging part of the expectations. So now I would write this term. I have, first of all, beta k plus 1, it is independent of measurements, okay? So this beta k plus 1 is independent of the measurements because the Kalman filter covariances are independent of the measurements, okay? So this beta k plus 1 is going to get outside this expectation directly. But what about x at k plus 1 given k plus 1? I know that this x at k plus 1 given k plus 1 is a function of y0 to k plus 1. Okay? So this is a function of y0 k plus 1. And I need, in the given condition, I have y0 k's. So y from 0 to k, they are deterministic, but I need to get rid of yk plus 1. Yk plus 1 is still random in these estimates. Okay? And I need to get rid of that randomness due to yk plus 1. from those estimates. So here, this is again a quadratic form, and that is why I am going to apply the same rule here that I have, okay? Except I need to keep in the conditioning of expectation and covariance operations the y0k, all right? So I would have here plus, this is going to be expected value of x at k plus 1 given k plus 1 transpose given y0k, okay, times this covariance, times, maybe I should write to the left more. So I have here plus expected value x at k plus 1 given k plus 1 given y0k, and I have transpose here wk plus 1 and the same expectation, expected value x at k plus 1 given k plus 1. Now you need to think about the Kalman filter estimate as a random function of the measurement yk plus 1, okay, and given y0k, okay. This is the expected term, it is this one, and then I would have the trace term plus trace this matrix wk plus 1 times the covariance of this estimate given covariance of the xk plus 1 given k plus 1 hat given y0k, okay. I close the trace. And I have one more term, and that is beta k plus 1, which is deterministic given the measurements. Beta k plus 1, okay? So then this term is okay. This term is fine, I can calculate it. This term is fine, but still I don't know this expectation and the covariance. And that is what we are going to do now. By the way, I think in this lecture I'm going to break a record for the longest video lecture that I recorded. Sorry for this. So here let us open a parenthesis and let us try to calculate these expectations. So here I need to calculate expected value of x at k plus 1 given k plus 1 given y0k. So y0k is given to us, and I need to think about the Kalman filter estimate k plus 1 given k plus 1 as a function of yk plus 1, and I need to actually calculate the expectation of it with respect to yk plus 1. Okay, so this is k plus 1. So now what I'm going to do is that I'm going to write the formula for this Kalman filter estimate. Expected value with respect to yk plus 1, this is going to be x at k plus 1 given k plus Kalman filter gain at time k plus 1 times yk plus 1 minus y hat k plus 1 given k. Okay, given y0k. Okay, it is just this expectation. So now x at k plus 1 given k is nothing but a function of y0k. Okay, because k is given here, so this is a function of y0k. So this is deterministic. And y hat k plus 1 given k is also a function of y0 to k. That means that this term is deterministic. The only thing that I need to take the expectation is going to be this term. Okay? And that is going to be, this is going to get out x at k plus 1 given k plus k plus 1 is a deterministic constant with respect to any measurement. It doesn't depend on the measurements and it's not random. So I have this expected value yk plus 1 given y0k minus y hat k plus 1 given k. Okay? But what is this expectation? This is nothing but y hat k plus 1 given k. Okay? So this is actually going to cancel, and I would end up with x hat k plus 1 given k. All right? So expected value of the Kalman filter estimate at time k plus 1 given y0 k plus 1 with respect to y k plus 1 given y0 k is nothing but the predicted estimate. Okay? That is pretty neat. But this is not really surprising, right? So I have here expected value. This estimate that the Kalman filter calculates is nothing but xk given y0 to k plus 1. This estimate is nothing but expected value of xk plus 1 given y0 k plus 1. Okay? Given y0 k. Okay? But this is again iterated expectations. So instead of doing this calculation, you can write this as an expectation here like this, and you can actually see that this is nothing but iterated law of expectation. Okay? So this is going to give me a single expectation, xk plus 1 given y0 k, but this is nothing but x at k plus 1 given k. So there are two ways to actually derive this. Now the next thing that I need is to calculate the covariance of the same thing here. All right? So I need to calculate the covariance of the same thing. Now what I'm going to do is that now write covariance of x at k plus 1 given k plus 1, and I have given y0k, this is nothing but expected value x at k plus 1 given k plus 1 minus mean of the same thing, expected value x at k plus 1 given k plus 1 given y0k, and I would take this into parentheses and I would multiply it with its transpose, and then I take its expectation with respect to y0k. Okay? But this thing I have already calculated, so that is going to be expected value of x at k plus 1 given k plus 1. X at k plus 1 given k plus 1 is this thing, okay? And then what I'm going to do is that I will subtract from this one, this expectation. But this subtraction of this expectation is going to cancel these predicted estimates. Okay, so here the only term that I would have is k plus 1, yk plus 1 minus y hat k plus 1 given k, and its transpose here, yk plus 1 minus y hat k plus 1 given k, transpose times kk plus 1, transpose given y0k. Here the Kalman gains are just deterministic quantities, okay? So they can get outside the expectation. The only thing that I'm left with is expectation of this outer product, okay? Yk plus 1 minus its mean given y0k times its transpose given y0k. But this is nothing but I have kk plus 1 and I have here kk plus 1 transpose, and in the middle I have the expectation of these terms given y0k. That is nothing but covariance of yk plus 1 given y0k. Okay? But what is the predicted covariance of yk plus 1 given y0k? We know this. This is the prediction covariance of the measurement yk plus 1 given all of the past measurements. This is going to be the innovation covariance. Okay? So this is kk plus 1 times sk plus 1 times kk plus 1 transpose. So these are again calculated using the Kalman filter estimates, Kalman filter covariances. So how nice. Here I would erase this we have the initialization here. And now I can substitute those results into my formula here. Okay? So I have Vk given k star y0k is going to be equal to minimize with respect to uk. I would have to write these, unfortunately. X at k given k transpose, I would have mk x at k given k plus trace mk sigma k given k plus uk transpose pk uk, and I would have this expectation plus this expectation is nothing but x at k plus 1 given k, and I would have wk plus 1. And I would have x at k plus 1 given k. There is a transpose here. Plus this trace wk plus 1. And I would have here that covariance. kk plus 1, sk plus 1, kk plus 1 transpose. And finally I have beta k plus 1. How nice. So now I got rid of all of the expectations here. The only thing that I have to do is to minimize this argument of this minimization with respect to UK. But do you think UK is only here? If UK is only here, then UK is going to be equal to 0. It really doesn't make much sense. Selecting the input 0 after all of these calculations. It really does not make sense because in these terms there is also an input contribution. Okay? So you see that here, these covariance terms, covariances are independent of input and the output. Okay? So these terms are going to go into the constant beta k. Okay? But in this predicted estimate, there is also the input term. We know that x at k plus 1 given k is nothing but a times x at k given k plus b times uk. So that is your uk here, hidden in this prediction. Okay? That is equal to minimize uk, and I would, let me write these terms. X at k given k transpose mk x at k given k. So then this term doesn't have any input in it. And then I will write this input related term, uk transpose pk uk. So I handled this, and then I have this term. Then I'm going to use the prediction covariance, predicted estimate formula. So I have ax at k given k plus buk transpose wk plus 1 ax at k plus 1 given k plus buk. So this handled just this term. Okay? And now I'm going to add the other terms. I have beta k plus 1, and I have here trace mk sigma k given k. This is independent of measurements because it's only dependent on covariances of the Kalman filter. And I would have this term plus trace wk plus 1 kk plus 1 sk plus 1 kk plus 1 transpose, and that's it. Okay? So now the only thing that, the only thing that I have to do is to minimize the right-hand side here. Only these two terms are dependent on the input. Okay? Let us minimize those quadratic terms with respect to the input. So in order to be able to do that, you need to remember the earlier theory that we have seen in the complete information case. In the complete information case, we have calculated such a derivative of such a function with respect to UK, and here we are going to do the same thing. Go back to that lecture and watch the similar part, and you can see that if I calculate the derivative of this term with respect to UK, then you're going to get 2pk times UK, plus if I take the derivative of this term with respect to UK, then I'm going to get 2 times B transpose WK plus 1 A x hat K plus 1 given K. There is a mistake here. This is K given K. Okay. It's K given K. Plus B UK is equal to 0. Okay? So now these twos don't mean anything, and I can actually collect UKs here into a single matrix vector multiplication, and then I would get, let us collect them. So I would put this B transpose WK plus 1 A x at K given K to the right hand side, minus B transpose WK plus 1 A x at K given K. This is equal to, I would collect all of the UK terms together. So I would have B transpose WK plus 1 B plus PK times UK is equal to just this. And then solve for UK star. UK star is equal to minus, this minus is here, and this thing inverse, B transpose WK plus 1 B plus PK inverse, and I would have the remaining terms. B transpose WK plus 1 A x at K given K. This remained here. Look at LK. LK in the complete information case. And LK there is just this constant matrix here. And in the deterministic case, in the complete information case, I had UK star is equal to minus LK xk. In the complete information case, I was multiplying xk with the gain LK. Here, the gain LK remained the same. But instead of the exact value of the observed state, here I need to use the Kalman filter estimate. Okay? So this UK star is nothing but minus LK times x at K given K. But we said that UK star is going to be a function of GK of Y0K. But I don't see any Y0K here. Y0K is hidden in the Kalman filter estimate. This Kalman filter estimate uses all of the current and the past measurements. So this Kalman filter estimate is a function of measurements between Y0 and YK. Okay, so we have achieved our control task, and this is going to be our optimal control feedback policy. All right? And it is actually a function of y from 0 to k. Okay? Now I'm going to substitute this optimal input into my Vk given k star. Okay? So Vk given k star of y0k is equal to, I have this term didn't change, I only optimized these two terms, okay? So I would keep this term as it is, x at k given k, mk, x at k given k, plus this term became just that one. I will replace UK with this optimal value, and it's going to be UK transpose of that one, x at k given k transpose, lk transpose, and I would have pk, lk, plus here I would replace uk with its optimal value, and it's going to be a minus blk times x at k given k. Okay, so this is going to be plus x at k given k, a minus blk transpose, and I have here wk plus 1, a minus blk x at k given k. Okay, and I have the rest of the terms plus beta k plus 1. Maybe some silence would be nice now. Plus trace wk plus 1, kk plus 1 transpose. So now you see here that these terms here, they all contain xk transpose xk transpose xk given k, and xk given k transpose x at k given k. So I can combine the matrices in the middle here. X at k given k transpose, I would first take this term, a minus blk transpose, wk plus 1, a minus blk, and I have plus lk transpose pk lk plus mk. And then I have x at k given k here, and I would have these terms. Okay? But you see that this optimal cost to go function, the value function, is nothing but a quadratic form in the Kalman filter estimate with this matrix, and I have some constant beta k. Okay, so this is equal to x at k given k. I will call this summation of these matrices as my wk, and I would call this is going to be x at k given k. There is a transpose here. Plus, I will call the summation of these constants as beta k. So now these equations remained from the complete information case. Okay? So in the complete information case, I had this recursion for wk, and wn was started as mn. Okay? But you see here that here, what I call wk is exactly the same right-hand side. Okay? So I have exactly the same backwards wk recursion. Okay? And furthermore, I have exactly the same feedback gain formula. This remains the same as well. Okay? So W's remain the same as in the complete information case, and LK's remained the same as in the complete information case. What changed here? The only thing that is changing is beta k. Okay? And this beta k update is going to be now different. So only the constant factor in the optimal cost changed. The W's remain the same as in the complete information case, and the control gains remained the same as in the complete information case. Okay? Only beta updates changed, and in that case we had beta k is equal to beta k plus 1 plus this trace trace mk, sigma k given k, plus trace, I had wk plus 1, kk plus 1, sk plus 1, kk plus 1 transpose. Okay? And how did we start the beta? We started betas from beta n. In the complete information case, beta n was equal to 0. Here it's not. We started it from trace of mn and sigma n given n. Okay? So we have solved this optimal control problem with partial information. Okay? And the only thing, one of the last only things here that remained is to calculate the final optimal cost. So I have started with Vn given n star, and we started this with an expectation of I have Cn of xn given y0n, and if this turned out to be x at n given n and mn x at n given n, there is a transpose here, plus beta n. Okay? We started with this, and then I calculated, so this is nothing but Wn, and this is beta n. So we started with Wn and beta n, and then we went backwards. Calculated Wn minus 1 when I have Wn here. Wn is given like this. And then I calculated beta n minus 1. And then we calculated Wn minus 2, beta n minus 2. And at the same time, I can calculate these control gains, and I can calculate my optimal feedback policies. And then we ended up at the end of this recursion at V0 given 0 star is equal to x at 0 given 0. I would have here W0, the last W that I find, x at 0 given 0 plus beta 0. Okay? Now the only thing to calculate J star would be to calculate this is a function of Y0, to calculate the expectation of this V0 given 0 star Y0 with respect to Y0. Okay? But this problem we already tackled. Okay? If I take the expectation of x at 0 given 0 with respect to y0, I would actually obtain x at 1 given 0, w0, x at 1 given 0. Okay? This is the expectation of x at 0 given 0 with respect to y0. Here there are no measurements in the past. Okay? So there is no conditioning here. But it's the same theory that you can calculate these expectations plus trace of w0. And here I would need the similar term to this here. I would have K0, S0, K0 transpose, and I would have beta 0. Okay? So this is my optimal cost in the partial information case. All right? So now we had complete information case, complete info. In that case, we had UK star is equal to minus LK XK, and partial info. In that case, we have UK star is equal to minus LK X at K given K. Okay? So now this type of controller has two specific properties, and these two specific properties are really important in stochastic optimal control. In this case, we considered a linear system, a Gaussian system with quadratic cost. But in some general non-linear, non-Gaussian with non-quadratic costs, the sum of the optimal control problems, stochastic optimal control problems, might have some similar structure. They might have different structure as well, but they are sometimes having a very similar structure to this type of solution. The first property of this type of partial info solution is the so-called separation principle. Separation principle means that estimation and control in the optimal estimation and control is separated. Okay? Separation principle means just that. Okay? So here we see that this controller, this calculation of this LK, it really doesn't require any estimated quantities. So here the control related quantity is this feedback gain LK. Okay? And this LK here, really, it really does not use any estimated quantities. Okay, you see that these W terms here, they are not dependent on the Kalman filter gains, okay, or Kalman filter covariances. All right. So here we see that the calculation of this LK, which is related to control, is separated from the estimator, which is the Kalman filter. Okay. So we see that in this control solution, estimation and control tasks were separated at the end. And this is the optimal feedback case in the linear Gaussian case. So this type of feedback policy, UK star minus LK x set k given k, we see that the dependence of this optimal input on y0k is only through the estimate x at k given k. Okay? The optimal input is dependent on the measurements y0k only through the estimate of the Kalman filter. Okay? These type of policies are called separated policy. Okay? So the outputs are not seen in this formula directly. They are only seen through this estimate. So I can write here other separated policy. This is a linear separated policy. And I can write UK star, for example, minus LK x at k given k divided by x at k given k. And I can here put some matrix. I really don't know. Let us say zk x at k given k transpose. This is a linear separated policy. No explicit output dependence. The outputs only appear through this estimate. And this is a non-linear separated policy. Of course, this is not optimal in our case, but still, we can have this type of policy which is also separated. This is a non-linear separated policy. Okay? And how does a non-separated policy would look like? In that case, in addition to these estimates, the outputs are also appear explicitly in the formula. And here I can write just VK, YK. If you look at such a policy, this is also a valid feedback policy because I have x at k given k, which is known, and I have yk, which is known. But here you see that the dependence of the optimal input on the outputs y0 to k is not only through this estimate. The outputs also explicitly appear in this formula. So this is a non-separated policy. Non-separated policy. Okay? And when we have a separated policy, we say that we have separated the estimation and control, and then we say that we have the separation principle applies to this optimal control problem. Okay? The second characteristic of this solution that we have found is that we see that in the complete information case we had xk, in the partial information case we had x at k given k. Okay? When in a partial information optimal control problem, if we obtain the solution, the optimal control solution, which can be obtained by replacing the complete information optimal control solution xk with its estimate, then we say that the so-called certainty equivalence principle applies. Okay? What is certainty equivalence principle? Here we see that the actual control law is not changing. These LKs are not changing, but in the partial information case, we are actually applying a control very similar or exactly the same as in the complete information case, except that we replace the exact value of xk with x at k given k. Okay? So we assume that this estimate x at k given k is actually certainly equal to the exact value of xk. Okay? That is why this is called certainty equivalence. That is why we say that in this case the certainty equivalence principle holds. All right? So here in some way we are saying that by applying this control in the partial information case, we are actually assuming that this x at k given k is the exact value of the state. Okay? So we are assuming that it is certain that this is the exact value of the state, and we apply the control in the complete information case. Okay? What might be a control rule where certainty equivalence principle does not hold? If this LK changed in the partial information case, if I had different LKs here, then I would say that the certainty equivalence principle does not hold for this problem. In optimal control, in stochastic optimal control, there are problems where separation principle holds and it may not hold, and there are some problems where certainty equivalence principle holds and where it does not hold. But linear quadratic Gaussian, in the linear quadratic Gaussian case, both principle holds. Okay? And there are actually some stochastic optimal control problem where these principles hold, but there are also some problems in which they don't. Okay? And the final thing that I can say here is that because we had the same WK recursion as in the complete information case, and because we had the same gain as in the complete information case here, we can investigate the steady state controller in the exactly same way as we did in the complete information case. Okay? So you can let the horizon n go to infinity, and you can calculate the steady state W bar and steady state control gain L bar, and then your steady state controller in the infinite horizon case would be minus L bar times x at k given k. Okay? And this L bar and W bar can be found just as in the same way as we did in the complete information case. Okay? So this actually finishes EE557. So I really did not want to exceed the time that is given to me, but without actually seeing this last topic, LQG control, we wouldn't be able to combine the estimation theory with the control theory that we have seen so far. So the course could be complete only with this theory, and I don't know how much that I have exceeded my allowed time here. So really sorry for this. So I don't know why in the pandemics, in these video lectures, I'm really spending a lot of time. I'm spending more time than necessary for these lectures than I would do in a real classroom. This is happening because I really cannot get any feedback from the students in this meeting room in the department. And as a result, I'm over-explaining things. So I'm trying to explain everything in minute detail. So and this made actually the lectures longer than necessary. So I'm sorry for this, and I would be happy that I'm happy that you tolerated this. So here, I would really wish that we have experienced this. You have experienced this semester under better conditions. So I really missed giving lectures in real classrooms. So I would hope that you would take more courses in this department, and we would meet in actually real classrooms, and we would meet face to face. Thank you very much for tolerating me during this semester, and thank you very much for taking EE557. That's all for this course. Bye.